Hello, my friends. In this video, we are going to study again the conceptual continuous random variables, such as the exponential random variable and the normal random variable. However, this time we are going to solve our applications using a programming language environment, mainly the main programming language that we use in our course, R. And of course, we need to learn a few built-in functions related to these distributions and random variables in R. Then we are going to solve a few examples using the programming language itself related to exponential random variable and normal random variable. And first, we are going to focus on the exponential random variable. So just like in the R session that we have covered about the conceptual discrete random variables like binomial and Poisson random variables, again, we are going to use the letter D as a prefix to the first few letters of the distribution, and then it is going to help us to calculate the probability density function of the related random variable. So basically, as theoretical, you know the probability density function of the exponential random variable with rate parameter lambda. It is easy to calculate it, lambda times e to the power minus lambda x for non-negative values, and for negative values, it is obviously 0. This function is the function in R which is represented with the comment dexp. Okay, so D stands for density, and exp is the first three letters of the exponential distribution. For example, if I want to calculate the exponential probability density function at 2 with rate parameter 1, then I can simply write dexp of 2 with rate parameter 1. So the first argument is the input of this function, which is x. This first argument here is the x value, and the second argument is the rate parameter lambda. Now, in the theoretical course, we have stated that when the rate parameter of the exponential distribution is equal to 1, we call this a standard exponential random variable. And if you just run this command line without the rate parameter argument in it, still you are going to get the same result, because by default, the rate parameter is assumed as 1. So this is the default assumption about the rate parameter. In fact, if you just write question mark DAXP and want to learn about the function itself a little bit more, you will see that the second argument is called the rate argument, and by default it is equal to 1. So even if you do not write anything for the second argument or for the rate parameter, it will be assumed as 1. However, if the rate parameter is something else, if it takes a different value, in that case you need to introduce that rate parameter. For example, if I am interested in calculating the probability density function with rate parameter 0.1 and probability density function at 5, this means dexp of 5 with rate parameter equal to 0.1. Now remember, in exponential distribution, the rate parameter is the multiplicative inverse of the expected value. This means this exponential random variable with rate parameter 0.1 actually has the average value equal to 10. So we are basically writing here the rate parameter, which is the inverse of the average value for the exponential random variable. Now, you know, actually, the probability density function values are not meaning anything. So they do not calculate probabilities. They are just function values. We can actually understand the relative likeliness of this value compared to any other value. However, in order to calculate probability statements about continuous random variables, first of all, the probability statement must be an interval probability. Secondly, we need to use the cumulative distribution function, right? which was the integral of the probability density function, which is defined here, and the closed form cumulative distribution function for the exponential random variable was equal to 1 minus e to the power minus lambda x for non-negative values. So all this function calculates the probability of an exponential random variable to be less than or equal to x. Remember now, for continuous random variable, equations do not have any probabilities, but inequalities, or the interval probabilities have probabilities. So they are logical probabilities in continuous random variables. So this less than or equal to a certain value probability can be computed by using this function if this x value is positive or 0. However, if it is negative, it is automatically 0 because it is impossible for an exponential random variable to take any negative value. Now, what is the built-in representation of this cumulative distribution function of the exponential random variable? Of course, this time the letter that we use as a prefix is p. So just like in the discrete random variables, if you remember, it was like d binom, p binom. Here we have dexp, pexp. So PEXP is the CDF, or the cumulative distribution function of the exponential random variable. So let's just say, if we want to calculate the probability of an exponential random variable with rate parameter equal to 1, the CDF of it at 2, or in other words, the probability of that exponential random variable to be less than or equal to 2, then we need to write probability PEXP to 1. So this is the probability of an exponential random variable to be less than or equal to 2 when its rate parameter is equal to 1. Now, just like in the DEXP example, if you do not write the rate parameter, by default, the assumption will be that it's equal to 1. So we assume a standard exponential random variable in that case. However, if somebody asks you the probability of an exponential random variable with rate parameter 0.1 to be less than or equal to 5, then you need to write PEXP 5 0.1. So you see all these probabilities, so this probability and this probability are the same. Now, my friends, there may be an issue here. So this, maybe I should have forgotten about writing the correct value here. Maybe I should change it in the actual document, because the probability of an exponential random variable with rate parameter 0.1 to be less than or equal to 5 is actually 0.3935 approximately. Maybe I need to correct this file with the corrected value here. So I'm just going to do this after recording the video. Now, another function that we need to learn is the QEXP function, which is basically the inverse of CDF. Now, actually, we have solved questions related to that. Remember, the CDF fx was indicating the probability of x to be less than or equal to x. And of course, there's a probability of these events, right, which is p. Now, we can ask this question in the opposite direction. So let's just say, for which value of x this random variable is going to be less than or equal to that value with probability p. So the question may give us the probability, and it may ask the threshold value x. Okay, so QEXP is exactly doing that. For example, here, let's just say we are interested in calculating the x value, lowercase x value, for which the exponential random variable with rate parameter 1 is less than or equal to that value with 0.5 probability. Okay, so this is basically the quantile function. Quantile, we are going to learn about this. Quantile means the separator of the random variables into two regions. So we are basically trying to find the quantile for 0.5 probability, which means half of the values that this random variable can take will be less than this value, and the other half is going to be greater than this value. So let's just say we have a random variable x with rate parameter 1, and we are asking this question: for which value of x the cumulative probability is exactly equal to 0.5. Now we are going to find this with the inverse function. So you see, if I am asking fx to be equal to p and I am asking x, this means I am asking f inverse of p, right? So the inverse function. And the inverse function of p exp is q exp. Why we are using q? Is it the letter that comes after p in the Latin alphabet? No, actually, q stands for quantile. Okay, quantile. Quantile means distribution separator. Distribution separator. And we are interested in the value which separates the distribution into two parts with 0.5 probability on one side and 0.5 on the other side. So, for example, for this question, we need to write QAXP 0.51, and this means the probability that a exponential random variable with rate parameter 1 to be less than or equal to this value will be 0.5. So exactly inverse. In fact, we can just copy this value and test it here. Let's just try to calculate PAXP of that value with rate parameter 1. So you get 0.5, which is exactly the inverse function. So QEXP of 0.5. So we introduce the probability to QEXP and we introduce the X value or the threshold value into the probability statement. Okay. All right. Or if you just do that, for example, QEXP 0.51, you will exactly get 0.5 because we have two functions which are respectively the inverse of each other here. All right. So you can also calculate the quantile at another probability. For example, again, let's just say we have a exponential random variable, but this time the rate parameter is 0.1. We are interested in the threshold value, x value, such that the probability of this random variable to be less than or equal to this value is exactly 0.95. Or in other words, 95% of the possible values that this random variable can take is just going to be less than this value. Okay. Now, again, you can use QEXP function. This time you are writing the cumulative probability as 0.95, but the rate parameter is going to be 0.1, which means the probability that this random variable with rate parameter 0.1 to be less than or equal to this value, 29.95732, is just going to be equal to 0.95. So as it is said here, you can also check this function that it will return 0.95 approximately. Now that we have learned enough about the comments about the exponential random variable, we are just going to solve a practical question here. So the first question here, it says, in a certain region, the time between consecutive earthquakes is exponentially distributed with a mean of 0.4 years. So the time between the earthquakes is on the average 0.4 years. Now, remember, this is not the rate parameter. This is the expected value of exponential random variable. And the rate parameter is the multiplicative inverse of that value, which is 2.5 earthquakes per year. So on the average, if the time between consecutive earthquakes is 0.4, this also means that on the average, 2.5 earthquakes are observed per year. All right, so we have determined the rate parameter in this question. Let's calculate the probability that the next earthquake to occur in 3 months. Okay, so what is the probability that the next earthquake will occur in 3 months? Now you see, we have defined this random variable with a yearly rate parameter. Yearly rate parameter. Therefore, we need to convert the question into yearly units. So how many years does 3 months make? It is 0.25 years. So the question is asking this. So let me show that to you in a paint file. Okay, the question is basically asking this. So let me make this a little larger, maybe. So we have the random variable x, which is exponentially distributed with rate parameter lambda that is equal to 0.25 earthquakes per year. I am sorry, not 0.25. I am very sorry. It is 2.5 earthquakes per year. And the question is asking what is the probability of x to be less than or equal to, so maybe I can write less than or equal to sign like this, to be 3 months, and 3 months makes 0.25 years. Okay, 0.25 years. Now, in order to answer this question, the command line that we need to write is PEXP of 0.25 with rate parameter 2.5 per year. And the answer is 0.4647 approximately. Now, so this is the command line that we need to write. So let's just say another question is asked. It asks us to calculate the probability that the next earthquake occurs after at least 5 months. So what is the probability that the next earthquake will occur after at least 5 months? So this time the question is asking the probability of x to be greater than, so it says at least 5 months. So we need to write 5 over 12 years, right? So 5 months means 5 over 12 years. And this is a tail probability. This is a greater than probability. Therefore, we need to calculate this as 1 minus the probability of x to be less than or equal to 5 over 12. Or you can simply write less in everywhere because it does not matter in for continuous random variable. Equations do not mean anything. Only inequalities are important for continuous random variables. So we are going to answer this question again with function 1 minus PEXP at 5 over 12 with rate parameter 2.5. And the answer would be 0.3528. Okay. Now, let's just say somebody has asked us the probability that the time to next earthquake to be between 1 and 2 years. Now, this is calculated as what? The simple way to calculate this is the probability of x to be between 1 and 2, right? So the time to next earthquake to be 1 and 2, between 1 and 2 years, will be equal to the CDF at 2 minus the CDF at 1, which is basically PEXP of 2 at 2.5 rate parameter minus the CDF at 1, again with rate parameter 2.5, and the answer will be 0.07534 approximately. Or you can use the integrate function and integrate the probability density function. Now remember, we need to define the probability density function as a function, the function that is to be integrated. So G is the function that I'm going to integrate, and it is defined as the DEXP function, the probability density function of the exponential random variable with rate parameter 2.5. And if I integrate the probability density function G from 1 to 2, again, I'm going to get the same result. Okay, so there are two ways. Of course, the way that we have used above is much easier than the way that we have used in below. In another question, we are going to practice the inverse CDF of the exponential random variable. It says the lifetime of the batteries from a production lot is distributed exponentially with 15 days average. Okay, so the lifetime of these batteries are exponentially distributed with average 15 days, which means the rate parameter in daily units is 1 over 15 batteries per day. So on the average, 1 over 15 batteries are dying out. They are exhausting. So on the average, 1 over 15 batteries per day are exhausting. So again, remember, the inverse of the average value of the exponential random variable is equal to the rate parameter. So we know the rate parameter now. It says, so this is a very large production lot. It says what lifetime exceeds the worst 30% of the batteries in the lot. Okay, which means 30% of the batteries are going to have a less lifetime than this certain value, and the remaining 7%, 70%, the better 70%, are going to exceed this lifetime. So it is basically asking the certain lifetime X for which the lifetime of the batteries are going to be less than or equal to this with 0.30 probability only. And this is the inverse CDF question. Therefore, we need to use the QEXP function with the cumulative probability 0.30 and the rate parameter 1/15. So according to this question, 30% of the batteries will have a less lifetime than 5.35 days. 30% of the batteries will die out, will be exhausted in less than 5.35 days. The remaining 70% are going to exceed this lifetime. Now, in the next question, it says, which lifetime is exceeded by the best 8% of the batteries in the lot? Okay, only the most successful, the best batteries, 8% of the batteries in the lot will exceed this lifetime. So the question is asking this, there is a certain lifetime which is only exceeded by a 0.08 probability, which means we are looking for the X value for which the cumulative probability is 0.92. Okay, so if greater than probability 0.08, then the less than or equal to probability must be equal to 0.92. So we are looking for the inverse CDF 0.92 at 0.92, again with the rate parameter 1/15. So you need to introduce your arguments correctly. Of course, the computers do not know everything. You need to know the theory behind the topic. And if you handle the theory, then you can also use the computers to calculate practical questions. Now, it says, write a comment which returns the lifetimes which are exceeded by 25% of the batteries, 50% of the batteries, and 75% of the batteries in the lot. So in that case, I am just going to do that. I will write QEXP. And remember, the rate parameter was equal to 1/15. And here I am just going to write 0.25, 0.5, and 0.75. So this means 25% of the batteries will not have a lifetime that is longer than 4.31. 50% of the batteries will not have a lifetime that is greater than 10.39 or 40. And 75% of the batteries will die out or will be exhausted before 20.79 days. Okay, so this is how we can do that. Of course, these three values, instead of introducing these three values as a vector in a combined function, you can use a much practical way like this. So you can write a vector from 1 to 3 and divide this to 4. And this is just going to calculate three values, 0.25, 0.50, and 0.75. In fact, these three values, the 25% quantile, 50% quantile, and 75% quantile of the distribution are also called quartiles instead of using the letter N. Okay, so let me write it here. Instead of using the letter N, if you write quartile with letter R, this means 25%, 50%, and 75% quantiles. So a quartile is basically a separator at quarters. Okay. All right. So that is enough about here. And one more question where we can see the plotting issue of the probability density function here. It says, plot the probability density function of the exponential distribution for lambda equal to 1.5, for lambda equal to 1, and for lambda equal to 0.5 over the same diagram, respectively with black, red, and blue colors. So of course we are going to plot this diagram. However, there should be a limit of the diagram that we draw. So from which point to which point we are going to draw it. So let's just say, since the average value of this is 1 over 1.5 and the average value of this is 1 over 0.5, so the average value is 2 here. So let's just plot these probability density functions from 0 to 5, so no more than 5. So what I'm going to do is I am just going to create a sequence from 0 to 5 with length 10,000. So this sequence, so I'm sorry, let me write it again. So this sequence is just going to be a very long sequence with frequent points from 0 to 5, and the length of this vector will be 10,000. And for all of these values, I am just going to use the plot function. And for all these values from 0 to 5, I am also going to calculate the probability density function of exponential random variable with rate parameter 1.5. And I'm going to connect these plot points. So the type of the plot diagram is a line. And the width of this line is just going to be 3. And the label of the x-axis is just going to be x. And the label of the y-axis, the vertical axis, is just going to be, of course, f of x, because it is a probability density function. And if I just plot that, you will see this is how the probability density function of the exponential random variable behaves. It's a decaying function that converges to 0, and the total area under this function is equal to 1, as you can see. And at 0, it takes the lambda value, which is 1.5. Now, of course, we are going to plot the other probability density functions as well. So if you again use plot function with, let's just say this time rate parameter 1, okay? But as you remember, this time we need to use color red. Therefore, we are just going to put another argument here and say the color is going to be red. If you run this function, unfortunately, you are just going to get another plot. So it is not going to be plotted over the previous plot. It's just going to open the plot in a new plot. Therefore, the correct function that you need to use is points for that. Okay. So if you plot the first diagram, and if you want to create another plot over that, this time you need to use the points function. If you do that, you are just going to see the plot diagram of the second exponential random variable with rate parameter 1 over the previous one. As you can see, as the rate parameter decreases, the maximum point of this probability density function increases, but the convergence of the tail becomes later than the convergence of the previous parameter. So if the rate parameter is greater, then the convergence is going to be fast. If the rate parameter is smaller, then the convergence is going to be slow. Why? Because if the rate parameter is slower, the expected value is larger, right? So the possible values that this random variable can take are going to be larger. Now, finally, we are just going to add another plot, this time with for a probability density function of an exponential random variable with rate parameter 0.5. And this time we are going to use blue color. And with the last line compiled, so you see this time the probability density function converges much more slowly than the previous ones. Okay, and the peak point is reduced. In all these three functions, the total area under these functions are always equal to 1. So, all right, so this is all I wanted to say about the exponential random variable. In the next video, we are going to study the R functions related to normal random variable.